Aloha. So, as promised, Chapter 2, Part A, Chemistry Comes Alive. Okay, then. Must study chemistry in order to understand how the body works. The body is made up of many chemicals. And, as stated before, physiology happens at the chemical level, inside cells and across their membranes, which that's the use of the word membrane is an issue here. When I was talking about this in the intro to anatomy section, the membrane was a sheet of cells, like the visceral and pleural pericardial membranes. In the context of the cell, it's the plasma membrane is the boundary between the inside and the outside of the cell, and that's something else. That's a phospholipid bilayer, and will be described later on in this chapter. So everything we do, physiology, occurs because of the chemistry. We're going to start off with just basic chemistry right from ground zero. This section is going to have the most basic of chemical and physical principles, and then we're going to move into very basic chemistry. We'll move through that, talk about the chemistry of water, because cells are mostly water. And the molecules of life are dissolved in water, so we must understand water and how it behaves with chemicals. Then we also have to study those chemicals, which is the chemistry of carbon, the biological molecules, protein, carbohydrates, fats, DNA, and then we'll take a look at those. We'll take a look at some general types of chemical reactions that occur. So we'll move from basic chemistry into the biochemistry. Biochemistry is the chemistry of biological molecules. And then that'll set the stage for us to understand cells and what happens inside cells. Matter. Matter is anything that has mass and occupies space. Has mass and occupies space. There's a lot of people, that's all they do, right? Have mass and occupy space. Matter can be seen, smelled, and or felt. I just like that description. And we weigh it. We describe mass as the amount of material present, and we can weigh it because gravity is pulling on it. So if you were instantly transported from the Earth to Mars, you wouldn't lose any weight. Well, you wouldn't lose any mass, but your weight, you would weigh 1/10, because Mars gravity is 1/10 of what it is here. Maybe we'll see that in the not too distant future. That would be so cool. Energy. Energy is sometimes what I'm lacking. The capacity to do work or put matter into motion, to change the state of matter, to manipulate it, to move it around, to have them interact. It takes energy. Energy does not have mass, nor does it take up space, but we can measure it. And here's something pretty obvious. The greater the work done, the more energy it uses up. Two general forms of potential energy, kinetic and potential. Kinetic energy is the energy of motion, movement. Literally, I just saw a car go down the street. It has kinetic energy. The faster it goes, the more kinetic energy it has. Potential energy is the energy of position, stored energy. If we were in the classroom together, what I would do is I would take an eraser and I would put it up on the board, on the top of the whiteboard, and I would leave it up there for a minute while I said, well, this energy, now this, I'd expend energy to get it up here. It took me kinetic energy to get the eraser up onto the board, and it'll stay there until it's disturbed. And then I go over there and I mess with it a little bit, and then it falls down, and then we convert that potential energy into kinetic energy, the energy of position while it's hanging on top of the board, the energy of motion, kinetic energy, when it falls. So these two can be interchanged, and we'll be talking about these. Mostly the potential energy we're going to be talking about is going to be stored in the chemical bonds of molecules, particularly the sugar molecule glucose. But also, a little bit we'll talk about the energy stored in the triglyceride molecule, which is fat. Matter. So we know the states of matter: solid, liquid. What does that mean? What causes that? That's one of the wonderful things about our little blue ball known as the Earth that we live on. Is water exists in all three states: a solid, a liquid, and a gas. So what determines which one it is? Well, you know, it's the temperature. If you cough enough, it freezes. If you warm it up, it melts. The temperature is the measure of the amount of kinetic energy in a substance. And we measure that with a thermometer, a thermo energy meter, measuring device, thermometer, usually pronounced thermometer. And what happens is the molecules that are moving bang into the thermometer and transfer some of their energy to the substance inside, and it expands and goes up, and then we read it. The higher the temperature, the higher the kinetic energy, the more violent those collisions, the higher the material inside the thermometer goes up, higher the temperature. Now, a solid. Solids have a definite shape and volume, so that doesn't change much, although some of them can be sort of plastic and flow. But the real definition is molecules fixed in space relative to each other. So they're in space, three-dimensional space, not very big space, and they're not moving relative to each other. Just think like if we were in the classroom, I would say, so you're all in three-dimensional space, not moving relative to each other. But each one of you is moving. I would point at somebody who's texting and say, well, they're moving a little bit. They're manipulating their phone, sending a text, and that person over there is taking notes. So you wouldn't be perfectly still. You'd still be moving. And so there's still some energy in a solid. The molecules are not moving relative to each other, but they're vibrating. And the more you increase the temperature of a solid, the more the molecules vibrate. Then, when they're no longer attracted to each other, when they gain enough energy to break whatever bonds are holding them fixed in space relative to each other, then they can start moving around in relation to each other. And that happens when class is dismissed and everybody gets up and goes their own separate ways and moves around a little bit, heads for the door. Somebody goes to get something to eat. Somebody else goes to another class. And somebody else comes up and asks me a question, which is a lot easier than sending emails, isn't it? So we can't do that, obviously. So that's why I live with my email. So that's a fluid. A fluid is a substance in which the molecules are in motion relative to each other. They have enough energy that they're moving around with respect to each other, just like students leaving a class. Now notice underneath there are two types of fluids. There's a fluid that is a liquid and gas. So what's the difference? Well, that's cute, that first definition, changeable shape, definite volume. That's true, but the physical description of a liquid is a fluid in which the molecules are transiently bound to each other. All right, let's stop there for a second. A fluid in which the molecules are transiently bound to each other. Now, if you look down here at the definition of a gas, you see changeable shape and volume. So okay, a fluid. You're like, wait a minute, gas, fluid, what? Yes. Now that we've defined fluid up here in this sentence, we have a much more technical understanding when we see it in the next two sentences. So a gas is a substance in which the molecules are in motion relative to each other. In a gas, they're not bound to each other. In a fluid, they are transiently bound to each other. Now, what does that word transient mean? Transient. Transient means more or less temporary. I got an email from one of you who told me that you were a transient student. Mm. We get those. We get a lot of you in the summer. Transient student is somebody who goes to another college or university and then just comes to TCC to take a class in the summer, and then they transfer it back to their home institution. So a transient student is one who's here for the summer and then goes back wherever. My daughter used to do that when she was going to A&M. Thankfully, she just graduated, but she would come home and she would take a class or two at Dallas Community College near where she lives. So transient, here now, gone later. So that means in a liquid, and then the liquid that is going to be important to us is going to be liquid water, where the molecules are transiently bound, temporarily bound to each other. So they form a bond, but they're moving fast enough that that bond can break. That bond has a name, hydrogen bond. We'll discuss that later. And if I would be demonstrating all of these topics with erasers, so I think I'm going to make a video in addition to this one of me demonstrating these topics. I'm just going to wait until my water comes back on. I think I posted in announcements. If you're listening to this summer, water is off since yesterday, so I hadn't had a chance to take a shower today. I'm not making a public video until I can clean up. So I'll get that to you. So a gas is a fluid in which the molecules are moving so fast they're not bound to each other. And one of the examples I give about this is, we live out here on the country roads, and I live way out in the middle of nowhere, and I'm 20 miles southeast of Waco and 20 miles northeast of Temple, 11 miles east of I-35. You can triangulate that and find me if you want. A little town called Durango, Texas. And when you're driving around the little roads here in the neighborhood, some of them aren't even paved, and you see somebody coming the other way, usually you wave to them. You're going slow enough, and you're in a familiar environment, and say, hey, well, there's George. I need to go look in on George, actually. But when you get out on the highway and you're going too fast, you don't have time to interact. No waving on the highway. And so that's like a liquid and a gas. When the molecules are moving slow enough, they have enough time to transiently interact. You wave to somebody. Whereas when you get out on a bigger, faster road, you don't have time to do that. And there is no interaction. That would be like a gas. So a solid, a liquid, and a gas, what makes a substance one of those states of matter is the temperature, the energy in the system. And then there are two ways of being a fluid, liquid and gas. Other forms of energy. You say, wait a minute, you just said kinetic and potential. That's true. These are forms of those energies. So chemical energy, stored in the bonds of chemical substances. That's the potential energy we're going to be talking about. That's funny when I say that. We're going to be talking about, right? Since you listen to this later, there is no talking on your part. It's just me. Electrical energy. Now, there's electrical energy when you plug into the wall, like you want to charge your phone. Those are electrons banging back and forth in the electrical lines. That's something different than biology as we know it. That would be interesting. A life form that uses like that kind of electricity at the outlet. Maybe I'll write a science fiction book about that. We're talking about the energy of charged particles. Molecules are particles that have positive or negative charges on them. And the two that we're going to be worried about the most are going to be sodium and potassium, which are both positively charged. So that's kinetic energy. Chemical energy is potential. Electrical energy is kinetic. Mechanical energy involves kinetic energy. Moving, like a muscle contraction. Radiant, or electromagnetic energy. This will not be a big part in our life, but it's kinetic energy. And this is the electromagnetic spectrum going, this goes from low to high in terms of energy. There's a couple below here, lower energy level. The lowest energy level electromagnetic radiation is radio waves. then microwaves, and then heat, which is infrared. What's the prefix infra mean? Infra. That's a good one to know because we're going to need that in the skeletal chapter. Infrared is below red, and when you get out of the infrared part of the spectrum, we get into the visible light, the lowest energy level of which is red, and it goes red, orange, yellow, green, blue, indigo, and violet. Indigo is one of my favorite colors. And then above the energy spectrum of violet, you get ultraviolet, ultra above. And then you get X-rays, and the highest energy spectrum electromagnetic radiation is gamma rays. So that is a little bit incomplete right there, but we fixed that. Energy form conversions. Energy can be converted from one form to another. That is the first law of thermodynamics. We'll get into that a little bit more a bit later. So, no, that's actually not. That's the second. These are the second law of thermodynamics. The first law says energy can neither be created nor destroyed, but you can convert it from one form to another. Like turning on a lamp converts electrical energy to light energy. Muscles. Moving a muscle converts chemical energy into mechanical energy. However, the energy conversion is not 100% efficient. You can't change 100% of one form of energy and end up with another 100% of another form. You'll lose some along the way. And I'm going to explain that more a little bit later when we get to the thermodynamics section. But since the energy is inefficient and you always lose some, where is the extra energy that you lost, that you were unable to harness? That answer is always the same. It's always the same. The energy is lost as heat. So no matter which way, how I throw you a test question about this, I say, so this much energy is converted and you capture that much energy, but you didn't get all of it. Where the extra energy go? The answer is always heat, which we can't harness by itself, but we can change. We can harness differences in temperature. Like if an area of hot or cold are separated, we can harness that. Matter is composed of elements. Elements are substances that cannot be broken down into simpler substances by ordinary chemical methods. All right? Ordinary chemical methods. That's the kind of energy we're going to be talking about. Ordinary chemistry. An element belongs to a particular atoms of an element. We haven't got to atoms yet, but the fundamental unit of the element is the atom, and each atom belongs to an element like hydrogen or helium or carbon or oxygen or nitrogen, sodium, potassium, and we'll talk about why. I'll talk to you about what makes those atoms of that element, and they can't be changed into other elements by ordinary chemical methods. They can be changed in nuclear reactions like that happen in stars. The big four that make up 96% of body mass: carbon, oxygen, hydrogen, and nitrogen. Those are the biologically most common molecules. Now we have some other ones that are important like sodium, potassium, chlorine, calcium, sulfur, phosphorus that make up the most of the other 4%. And they're very important. We just don't need them in as large quantities. And then we have trace elements, things like iron, zinc, magnesium, that we need very much so, but in very, very small quantities, hence the name trace elements. And we have something called a periodic table. Oh, I thought there would be a picture of a periodic table. No, we're not quite there yet. But it's a list of all the known elements. Now, you've probably seen a periodic table, and you're looking at it saying, that's weird looking. Why is it that shape? Well, one of the things is that when I ask you that question, well, why is it that way? You can tell yourself, he's about ready to tell us, because I will. All elements are made up of atoms. There we are, which are the unique building block for each element. So what makes an atom of hydrogen, hydrogen, and an atom of helium, helium. We're getting there. We're getting there, see? Very close. These are the smallest particles of an element with the properties of that element. So the one atom of an element is going to chemically act like a whole big pile of it. And its identity is what gives each element its particular, or maybe even peculiar, physical and chemical properties. That is, chemical properties, how does it interact with other atoms of its element, and how does it interact with atoms of other elements? That's chemistry. How atoms interact with other atoms. Physical traits are like what's the melting point? What's the boiling point? What's its density? How much matter can you jam into a particular space? The atomic symbol is a 1 or a 2-letter shorthand for each element, and some of them are obvious nicely. O for oxygen, C for carbon, H for hydrogen, N for nitrogen. And then we have, you see, sodium is Na. And for years, I would be like, all right, how come Na is sodium when there's not an N or an A in the word sodium? Little things like that bother me. I'm like, come on now, there's got to be an explanation. And one day I decided I'm going to find out. I can Google it. And it turns out that the Greek name for salt is natrium. Natrium. And so since salt is sodium chloride, sodium got named Na from the natrium from which it comes. And the same thing with potassium. There's no K in potassium. You see a K there? I don't. And it comes from kalium, the Greek word for potassium, which they used in making fire, whatnot, back in the day. Now, if today is the first day you've seen sodium abbreviated Na and potassium abbreviated K, then if that's the first time, here it is. Boom, introduction. If it's not, well, then lucky you. Now, as I speak to all of you, and I think I have almost 50 of you to start with, some of you are very familiar with chemistry, and you're like, oh yeah, sodium, potassium, they're my old friends. Some of you are new to chemistry or haven't had it in a while or ever at all. So for those of you who really know this stuff well, if I sound like I'm, talking about stuff that you should probably already know, just know that I'm trying to not leave the other people behind. Got to get you all to the finish line, remember? That's my goal. So here we go. The oxygen is the, by mass, largest element in the human body, and actually in all living things, followed by carbon, then hydrogen, and then nitrogen. In what form do we find oxygen that makes up 65% of our body mass? In what form do we find that oxygen? Where is it? Where is all this oxygen? Well, here is a critical thinking exercise for you. Some people will say, well, in oxygen, we breathe oxygen, so it must be that. That makes sense. And sometimes you might want to just stop there and say, yep, that makes sense. I'll accept that answer. But then if you'll think about it, how much does one of your breaths weigh? If you took a deep breath and then exhaled, what's the mass of that exhaled gas? It's not very much. I'm not going to tell you how much I weigh, too much. But that's not a very large percentage of it. It's certainly not 65% of it if you average it all up. So what's the most common substance in living organisms like humans? Then you would say water. And what's the formula for water? H2O. And so the oxygen that makes up most of the mass of the body is the oxygen in the water molecules. How about that? So you have to, but when I said by critical thinking skills, was asking yourself, all right, so the oxygen I breathe, does that make sense? No, not really. So keep thinking, keep asking the next question. don't give up when you get to an answer that you like. Carbon forms the backbone of all the major biological molecules. There's four: carbohydrates, proteins, lipids, which are generally fatty molecules, and nucleic acids like DNA. We find hydrogen in almost all atoms as well. Thing is that the mass of hydrogen is not that much. Uh, we're going to come up with a number for these things. The mass of oxygen is 16. The mass of hydrogen is 1. So H2O, a water molecule, weighs 18. 16 of that comes from the oxygen, only 2 from the hydrogens. And then nitrogen we find in pretty much just proteins and nucleic acids. Here's a list of some of the other elements. The ones that are going to be most important to us are going to be sodium and potassium. We will deal with calcium toward the end of the semester a bit. Phosphorus, we're only going to deal with it as a P, pretty much for just one or couple of occasions. There's a molecule called ATP, which is a energy storage molecule where the P stands for phosphorus, or actually stands for phosphate, which is phosphorus and some oxygens. We'll see sulfur once, chlorine a few times here and there, not too often. I don't think in AMP1 we're going to talk much about magnesium, iron, or iodine, but you will talk about iodine and iron in AMP2. So that is the basic introduction to physical and chemical properties. And I'm going to come back next and talk about the subatomic particles, whatever those mysterious things are. So, turn off. There we go.